Greetings, chemists. This video will be the last video in the equilibrium series, and we'll be discussing factors that shift an equilibrium or disturb an equilibrium. So we talked already about what it means to be at equilibrium. Now we're going to look at things that interfere with or try to interfere with that equilibrium. This main work was done by a French chemist named Le Chatelier, so it's named after him. It's called Le Chatelier's principle. So we're going to start with an equation of a chemical reaction. I'll take some hydrogen and we're going to react it with some nitrogen, and it will form an equilibrium between those reactants and the product, which is ammonia, which is a very common fertilizer. So this is how you make fertilizer. And this happens to be an exothermic reaction, so I'll put a delta H on the product's side. And let's go ahead and balance it. And we'll have 2 here for the 2 nitrogens, and that's 6 hydrogens, so we'll need 3 over here. So here is our balanced equation for the synthesis of ammonia. And now I want to picture what this looks like. So if you were to actually run this reaction, you would need a reaction vessel. So let's make a big tank that we're going to conduct this reaction in. It would have to be closed because these are all gases. And let's say we have a pipe leading off the tank to our reservoir of nitrogen. This is what we're going to use to pump nitrogen in on one side. And let's suppose we have a tank over here, and we'll fill it with hydrogen. It's going to pump in on this side. And let's further suppose that we have a tank for the ammonia itself. And we'll suppose that all of these pipes have a pump and a valve, so they can pump the nitrogen in or out, or the ammonia in or out, the hydrogen in or out. And let's also suppose that at the top, we have a big, heavy piston that we can plunge into and out, so we can squeeze down on this reaction vessel. And let's suppose at the bottom we have a heat source. Now, what I really need is a variable heat source that can go high or low. So let's just put a box here, and I'm going to put heat/cold to say that we could make this hot or cold depending on what we need at any given time. Okay? And let's suppose we open up the valves once and we let hydrogen and nitrogen and ammonia all flood in at the same time. And they're all bouncing around in there and colliding. And we have this idea from before that what will happen is as they collide, remember collisions are what cause a reaction to happen, the nitrogen and the hydrogen will collide and they will form this NH3. But as the NH3 bounces around, of course, according to this reaction, it will spontaneously fall apart and split back into nitrogen and hydrogen. And this is happening at the same time, simultaneously. And so every time this happens, as this goes on, we eventually will reach an equilibrium concentration that does not change, where the amount of N2 is no longer getting bigger, the amount of H2 are smaller, bigger or smaller, H2 is not gaining or losing, and H3 is not gaining or losing. That they are continually reacting. They don't stop reacting. The concentrations become stable over time. All right? And that's the situation. We close the valves, and that's what's going on there. All right? And then once you're at equilibrium, we're gonna ask what would happen if I pumped some more H2 in. So let's say I open a valve over here and the pump pumps a couple extra H2 particles in. What you would see, and what Le Chatelier noticed in reactions like this, is that when he pumped more of this guy in, think about it, there's more H2 bouncing around and hitting the nitrogens. The collisions are happening more frequently just because the concentration of H2 has increased. And what will happen is those reactions will start to happen faster. And so the H2 and N2 will react faster and will produce more NH3, and that forward reaction speeds up. Now, it speeds up briefly. It doesn't stay speed up because as they react, remember when an H2 reacts, it takes away some N2s. Actually, it's 3 to 1, but I'm not going to worry about ratios right now. You just get the idea that some of this goes away. we get more NH3, and eventually we will get back to that equilibrium concentration. And once we get back to that equilibrium concentration, the reaction stays there. It gets just like, fine, I got perturbed, but I went forward a little bit faster until I got back to equilibrium. Now let's suppose it were possible to run that pump the other way and suck some H2 out of here and pull that out. Well, if we pull the H2 out, there's less H2 bouncing around and bumping into the N2s. And when we pull, and that's going to make that forward reaction slower. And if the forward reaction is slower, well, we're producing less NH3. But it doesn't change how much NH3 is falling apart, right? The backward reaction is still going at the same rate. So NH3 is spontaneously falling apart and turning into N2s and H2s. So if the forward slows down and the backward is still the same rate, then over time, these NH3s are going to disappear at a faster rate than they are being produced, and we're going to get some more H2 and N2, again, until we get back to the equilibrium concentration. So a disturbance in the equilibrium means we suddenly adjust some factor. In this case, we were adjusting the concentration of one of the reactants, and that changes the rate of that reaction briefly until, and then the reaction shifts. One direction essentially wins the race. One direction is producing or reacting faster until we get back to that same equilibrium concentration. So what I like to think of it, here's my model. Imagine that this is the equilibrium concentration here. And we have the products are pushing this way. These are the products. This is the NH3s. They all push, right? And here on this side are the H2s and the N2s. And it's like almost like a reverse tug of war, like they're both pushing against each other, right? Because the products or the reactants push towards the products, and the products push backwards towards the reactants. If I were to take away some H2s, let's say there's a whole bunch of H2s that are all pushing in a line, and a whole bunch of N2s, and a whole bunch of NH3s that are all lined up like dudes on a tug of war. And let's say I take away an H2, well, all of a sudden, and it was balanced before, and all of a sudden now I've removed the balance, right? I've taken away some that were pushing from this side. Well, if this side pushes less hard, this side pushes harder, the equilibrium will shift to the left. What does that mean? It means for a brief instant, we are producing more, we're taking more NH3s are falling apart and turning into these guys than are going forward. And when that thing moves backward, more of these are formed and more of these are used up temporarily until we get back to our equilibrium concentration. If I were to add extra N2s on the left, like pump more nitrogen in from this side, let's say, I'd be filling this up with N2s, and they would be reacting faster, right? Because they're clunking around with more collisions, right? Every time there's more N2s, there's more hits, more collisions. And more collisions, well, that would be like my tug of war analogy. That'd be like pushing harder to the right. Well, if I push harder to the right, more of these guys are going away, more of these guys are being formed. More reactants are used up, more products are formed until we get back to our equilibrium position. It will always get back to that concentration in the middle. Okay? So when we talk about the concentration of the species involved, what we're saying is you add more of your type, your product, let's say, that will create a push towards more reactants. If you were to pull products out, that would create a push in the other direction towards more products. If you were to, and the same thing on the reactant side, if I remove reactants, the push is towards the reactants to create more reactants. If I add more reactants, the push is towards the products because the reactants are on that side. Now, let's talk about the other things I set up here. Let's suppose I adjust the heat, the temperature. Let's suppose I add it, like I'm heating from the bottom. What will that do? Well, notice here that every time these guys react, these reactants turn into products, they create heat. Every time these products turn back into reactants, we lose heat, right? Heat can be treated like a product in this case. So if I heat this system, I'm adding in a product, and it's exactly the same as if you had added in some NH3. So heating this equilibrium actually shifts the concentration to the left, to the reactant side. So I would actually, if I heated it, I would expect more H2s and N2s to start appearing and more NH3s to be going away, simply because heat is here on the product side. if I added in that would make the backwards reaction faster. Okay? What if I cool it off? What if I take heat out of the system? If I take heat out of the system, well, heat was a product. That's like pulling guys off the line over here. You could imagine a bunch of delta H's stacked up. Not that they are molecules or anything, but if you're visualizing it, maybe this is a way to visualize it, that if I were to pull some of these guys off the line, this side would not push as hard, the reactants would still be pushing as hard as they were, and the forward reaction would speed up, and I would be producing more NH3 and less H2. Okay, so that's how heat and cold would affect the system. What about the piston I put in there? Well, if the piston squeezes on this reaction, it makes less space. How would space affect this? Well, first of all, this is a pressure effect. And pressure, we've talked about before, really only has a noticeable effect on gases in this particular case. Pressure squeezes them, and because they fill their container, increasing the pressure will really have an effect on the gases. Now, let's look at, this is going to have to do with numbers. Every time, let's look, 3 hydrogens combine with 1 nitrogen, they turn into 2 NH3s. Let's watch that. If I lose 3 hydrogens, 1, 2, 3 hydrogens, and 1 nitrogen go away. There, I did it. And then I put in 2 NH3s. Now, NH3 is a big molecule, but it's what we'll think about is in terms of number of molecules in the system, right? Like H2 is a molecule, N2 is a molecule. Every time I go forward, I lose 1, 2, 3, 4 molecules, and I gain 1, 2. So there's a net loss in molecules in the forward reaction. In the backward reaction, it's the opposite. Every time it goes back, I lose 2 of these, and I gain 1 and 3, or a total of 4. Think about what happens when I squeeze. When I squeeze the pressure in, I'm creating less space. That's a favorable condition for the right side, right? Every time these react towards the right, we create less molecules. Less molecules fit more easily into a smaller space. So when the pressure on this reaction goes up, it will actually shift the equilibrium towards the side with fewer moles of gas. If I were to pull the piston out, that would tend to shift the equilibrium backwards because now I have room for the side that has more molecules of gas. So it would shift from 2 moles to 4 moles of gas. I'm sorry, I didn't mean to put a scratch on there. Okay, so let's talk about this. If we were to make some rules, increasing the concentration of the reactants shifts the equilibrium towards products, the concentration of products. And the reverse is true. Decreasing the reactants would shift towards the reactant side. If we increase the temperature, we shift, let's just say increasing temperature shifts the equilibrium to the side. It will depend, right? I happen to have an exothermic reaction here. So if we increase the equilibrium on an exothermic reaction, it would shift towards the reactant side. But it essentially shifts the equilibrium away from the delta H. So it depends on what the delta H is the product. Let's say increasing the temperature, and I'll, English hard, shifts equilibrium away from the side of the reaction with the delta H, and increasing pressure shifts equilibrium towards the side with fewer moles of gas. And I ran out of space there, so I apologize for my small writing at the end. So, all together here, if I'm looking at this, sorry, I'm having a brain fart there. The reaction responds by trying to minimize the change. If you create a change that would push forward, right? If you add too much to the left side, it tends to push forward to create more on the right side. If you take away something from the right side, it tends to push forward to fill that back in on the right side. So these are effects that tend to minimize these disturbances. Okay, complex principle. I hope you did all right with that one.